Whistler 100 watt power inverter. It just plugs into a cigarette lighter type outlet in a car, so it gets 12 volts in, and the output is 115 volts. It's supposed to be 60 hertz. This is definitely not a pure sine wave inverter. It's probably modified sine wave, which is like a stepped approximation to sine wave or square wave. Going to plug the kilowatt meter into this, and we'll see what kind of voltage we're getting. It may not be accurate because, like I said before, this is not a pure sine wave inverter, and certain meters cannot tolerate that and will not give a proper voltage reading on a non-pure sine wave output. So as you can see right now, we're hooked up to the outlet, and we're getting 121. And our frequency is right about 60 hertz where it should be. So I'm going to unplug it from this and plug it into that little inverter. I'm also going to run this little fan off of it and compare it to how it runs on the regular power. And I'll run this Holmes heater on fan only. Obviously this thing will go into overload instantly if I turn the heat on. But let's see what this stuff does. I will also hook up the Fluke True RMS clamp meter to this inverter, but got the kilowatt meter hooked up, and surprisingly it is actually giving accurate voltage. 123 point. Now it's fluctuating a little bit, but it's right where it should be. Let's see what our frequency is according to this. Yeah, this is where we're starting to have some problems. 11.8 hertz. Don't think that's what it's putting out. Like I said, it's not a true sine wave, so this is not measuring certain things accurately. Yeah. And we're getting about 123.9 volts with the Fluke meter. That's pretty close to what the kilowatt meter was saying. Unfortunately with this, you cannot get a frequency reading with the probes. You have to use the clamp meter for that, or the clamp. And I will show you. Yeah, it's not going to register anything. Once I'm done testing these fans out, I'm actually going to hook up one of those TVs to this and see if it'll run one of those. So stay tuned for that. But right now, we're going to start off with this, and I will test it on regular power first, and then I'll plug it into this. And I will plug this converter, which I haven't showed this yet. This is basically just it plugs into the line power, and it converts the 120 volts AC to 12 volts DC, which you would normally get out of a cigarette lighter car outlet, and then I have this plugged into it. So I'm going to try plugging this in, or plug in the converter into it with the fans running on it and see how much it draws. Yeah, that outlet this is plugged into on this power strip is a little flaky. I have to move it up one. And then I'm going to plug the kilowatt meter into this and then plug the fan into it and see if we get the same reading or a different reading. I know that there's going to be a little bit extra power being drawn because of this thing draws power itself. So we'll see what the difference is. And of course the inverter draws some power too, so with it plugged in like this, with the converter and the inverter after it, you're going to get a little bit of a draw. We're drawing 6 watts, 0.08 amps. So let's see what we get with the fan. Alright, I got the fan hooked up here first, and I'm going to unplug the converter and actually plug it into the kilowatt meter to see what it draws on line power. Okay, so fan is plugged into line power. This just has a little 2-pole shaded pull induction motor. I'm going to turn it on. Probably hear the speed it's running at. And we are drawing 17 watts, 0.21 amps. Turn that off. And now I'm going to plug the converter back in, and we'll see what we get. Okay, the fan is plugged into the inverter now, and I have recorded some information here. The fan on line power was drawing 17 watts and 0.21 amps. The converter and the inverter alone draw 6 watts and 0.08 amps. Now let's see what we get with the fan on as well. Sounds like it's spinning at the same speed. And we are getting 23 watts and 0.30 amps. I forgot to do power factor. With the fan running on the inverter and converter, we have a power factor of 0.63. Turn that off. And our power factor is pretty low, even with the fan off. Obviously this is going to completely change what the power factor of the fan is. Now I'm going to see what the power factor is with the fan just plugged into the kilowatt meter. Alright, fan is running on line power again, and we're getting a 0.65 power factor, which is normal for a shaded pull motor. They're pretty low when it comes to power factor. Try and get a sound of the motor humming as it comes up to speed. Can't really hear it. See if it's any louder on the modified sine wave inverter. Alright, here we are on modified sine wave. You probably couldn't really hear that on camera, but when I put it up to my ear, it definitely has more of a buzzy sound to it, and it's also a lower pitch, so I don't think this is putting out exactly 60 Hertz. I think it's a little bit lower. Now what I'm going to do is unplug the fan from the converter, plug the kilowatt meter into the inverter, and then plug the fan in after that. So we'll see what our readings look like then. But before I do that, I want to do the math here and see what the difference is between the power draw with it all going through this before it gets plugged into the kilowatt meter. Okay, after subtracting the parasitic draw from the AC to DC converter and the DC to AC inverter, you can see we have 17 watts and 0.22 amps. Very close to what the fan drew on line power. It also drew 17 watts on line power, so that's the same. And 0.21 amps on line power, and then 0.22 amps on inverter power. So slightly higher amp draw, but really it's pretty much the same. So now let's hook up the kilowatt meter to the inverter's output. Here's another close-up of me trying to get the sound of the motor on the modified sine wave inverter. Alright, kilowatt meter and fan are plugged into the inverter. There's our voltage, and that's pretty much the same as what the fluke meter was giving us. And we'll go to watts and turn the fan on. Okay, we're running normally, drawing 17 watts, 0.29 amps. It is fluctuating quite a bit for some reason. And go back to watts. About 16 to 17 watts. Went down to 15 there, now it's back up to 17. So yeah, it's fluctuating more. And keep in mind that since this is not a true sine wave output inverter, that the readings we're getting right now are probably not accurate. I was just curious to see what they would be with the kilowatt meter plugged into the inverter's output, because I knew that was going to affect it in some way or another, since again this is not true sine wave and this is not a true RMS meter to the best of my knowledge. Alright, and we can compare that to what we were getting before, about 17 watts and 0.21 to 0.22 amps. Now we're getting about the same wattage reading. It's fluctuating. Amps, definitely higher, and again it's fluctuating. But that should probably not be taken seriously. Let's see what the power factor is. It's really low right now according to this. And we're currently putting out 37.8 hertz, 38.6. Yeah, the frequency measurement is not accurate at all on this thing. And you can see that it's different from what it was before with a load on it, so that's interesting. I wish I had a scope meter so I could see what the output waveform looks like on this thing. We'll test the heater next. Alright, here we are looking at the output frequency again. As you can see, it's saying DC right now, and it's kind of fluctuating. Right now it's saying 8.1 hertz. So that is totally inaccurate on this thing's output waveform. The fact that it actually thinks it was direct current for a short time there. Alright, this is a 1500 watt heater. Has exactly the same type of motor as that little fan did, or does, and yeah, it's just a 2-pole shaded pole induction motor. 1500 watts on high setting. This has fan only and then low and high heat. So running it on heat, it'll just shut that thing down immediately, but we'll try it on fan. See how it runs. So you could probably hear that buzzing doesn't sound right. I mean, if you're used to what a 60 hertz hum is, that sounds different. Try and get that from the back. So here it is on the inverter. Here it is on line power. I think it's spinning at about the same RPM. Well, let's see what we're pulling. About 20 watts. And if we turn the heat on, obviously it goes way up. We'll keep that off. And just run the fan. 0.23 amps. And here we are running on the inverter again. There's our wattage. Remember to subtract 6, so that would be 20 watts. Exactly what it was pulling before. And amps. Inverter's not getting warm yet. Just for fun. I want to see what happens if I turn the heat on. Yeah, it just shut down instantly. The red light's off on the inverter, and you can see I still have that on. So let's see here. Alright, inverter's unplugged, and it's interesting. The inverter was still drawing a little bit of power even when it was in overload mode. Because now it's down to 4, and when the inverter was still plugged in, it was at 6. Now we can try this HV12. This one's got a bigger motor. It is a 0.9 amp motor, I believe. Let me see. Yeah, it's a 0.9 amp PSC motor. Right now I have it plugged into line power. We can see how it sounds. Oops. What did I do wrong? Got it plugged into line power right now. Let's see how it sounds. nice and quiet and smooth. Alright, now we're plugged into the inverter. Now notice it does not sound right. Medium, low. Speed isn't that bad, but that motor is not liking that. See how many watts we're drawing. Alright, it's running it on high, surprisingly. Let's try a bigger fan. We got a 14-inch and a 20-inch. Here's the 14-inch version with the 1.5 amp motor. Don't think it's gonna run this. Nope, it cut off right away. Let's reset. And we'll try a lower speed. Light is on. Let's go to low. It lasted a little tiny bit longer, but nope, it's not going to run this one. It might be able to run it if it was up to speed, but there's no way it's going to start it. I don't expect this to work either. This is a 20-inch high velocity fan. This one starts on low. Let's see what happens. Yeah. Barely moved. So yeah. I think that was pretty interesting. Tried hooking this old Century antique ceiling fan up to it, and it could not get that moving at all. So, alright, I know I said I would try a TV. It's plugged in, lights on, let's see what happens. Instantly shut off. Will not run a CRT, that's for sure. Here's a Lakewood SPC LT12 high velocity fan. It's got a Samsung PSC motor in it. And I'm also going to test this one on the inverter and compare it to how it runs on line power. So right now it's just plugged in to the kilowatt meter, which is plugged into the power strip. Test amps. I'm not going to be able to run this fan on high when it's on this, but it can only run on low on this thing. So I'm just going to do low here. .63 watts, 0.53 amps. Here's a sound from the motor starting up on line power. Alright, now I'll get the inverter hooked up. Now the fan is plugged into the inverter, and we'll see how much it draws. Here we go, starting on low. We're getting 75 to 76 watts. And you have to remember that the converter and the inverter have a parasitic draw, so that number is going to be higher than it should be, obviously, because these devices themselves are also drawing power, not just the fan. So let's go to amps. 0.97. Okay. Okay, so on line power, that fan was drawing 62 watts and 0.52 amps. Now, the next test was with it plugged in through the converter and inverter, which have some parasitic draw, so that's why it's significantly higher. But now we go down to the bottom line, which is where I subtracted the parasitic draw from those two devices, and we're getting 69 watts and 0.44 amps. So the wattage went up compared to how it was when it was just plugged into line power, and the amperage actually went down. So that's interesting, and you can hear it's still kind of noisy. Inverter's getting a little warm, but it's nothing crazy. Let's see what happens if I turn it up to medium. Wow. It's actually working on medium.